what I've got here is the same queue interface that we had when we did the array version of things. And now we need to do the linked list implementation instead. So I'm going to make a Java class called queue with a linked list underneath it. And I'm going to say that that thing needs to do everything that our queue interface does. For whatever types of things we want to put on the queue. And you have to repeat that word for the kind of thing there. And now it complains and it says, well, you promised to do all these things, but you haven't actually done what the interface said you're supposed to do. So there's the methods that we have to write. Okay. Before we get to the methods, we should worry about the data. So from our diagram, what do we need for variables? So we need front, I'll put in there, and count. Count is easy, count is an integer. Needs to be private. How about front and end? They're nodes, so we'll do private node front and private node for the end. Where's the node class? Gonna have to make the node class. We don't have one yet. Should we make it inside or outside of the class, of the link class? Anybody else have to see them? The nodes are really internal business, so we'll make the node class inside this class so that nobody can see it, mark it as private. What's a node class going to have in it? It's going to have whatever we're actually attempting to store. What type of variable is that going to be? Whatever we put on the list, but we're going to be consistent. Dogs, cats, people wanting to buy tickets. And what else? The next thing in our chain, what kind of variable is that? So from the diagram, one node refers to the next one to find. It's a private class, so I'm not even going to mark those variables as private. I am going to make a constructor. And the easiest thing to do for the constructor is to always send in the thing to store. Set that variable and always make a new node that's got nothing in it. So we'll set thing to store to whatever was coming in, and we'll set the next variable to hook it in later. How about getters and setters? We could write get next and set next, but those variables, if you put a setter in to set the next, the setters that we've written when we did this before never actually bothered to check the data to see whether or not it was correct, which is the normal role of a setter. All that the setter did was say, okay, I'll just accept that variable, I'll hook this thing up to the variable. And so in this case, the only thing that we're really using that node class for is not to control the values, but just to group them together. Okay? And so if we're grouping them together, we won't bother with getters and setters. We'll just allow whoever's using them to use them directly. Okay, so that's all that's going to be in the class. It's just a grouping mechanism for those two variables. Okay, so we've got those variables defined at the top of the class. We need a constructor for this class that initializes those variables. What should front have for a value? Nothing on the list. That says no variable at all there. Same thing for and. Starts out not referring to any object at all, and count happens to be 0. Well, if we're keeping count, then I guess that makes returning the size easy. We'll just send back whatever the count is for how many we've got. So let's talk about the case where somebody says, I want to join the lineup. What are you going to do with them? From the diagram, we've said we got another person comes along, here's F comes along and says, I want to join the lineup. From the diagram now, if this is the kind of thing that you're storing, those E-type items, then the thing that's missing from the diagram is I need a new node in order to do this. So I'm going to need to make one of those nodes and remember it and hook that thing up to F to start with. Okay, so in my diagram I have, I'll do it in the order I did it, make a new node, have it remember that thing that we're trying to put onto the chain, and then give that variable a name, maybe not the best name, but I'm going to call it new node, and the kind of variable is a node. So this is how many times can I say node on one line. Okay, so now we've got new node remembering that thing. How do you get it onto the chain? This is the place that you're interested in. Who's remembering that place? And so we've got to change the end variable to refer to the same thing that new node is referring to. So take the value that's in new node, copy it into end dot next. So take the value that's in new node and copy it into end dot next. So the effect of that, if you take that value and put it in end dot next, you've drawn that line. Now what has to happen?
And equals new node.
And is no longer, this is the inappropriate place now for and. If there's another one on there, and has to slide and stand underneath that one. Who's holding on to that one? Either way, two variables are holding on to it now, but we'll use the same one. So and equals new node. What else has to change? We played with at least one of the variables on the chain. So let's go up to the top of the class and ask the question, does front have to change? We changed and. What about count? Yes. So there's always a good check anytime you change one of the variables in the class. Go back up and ask yourself the question, I wonder if any of the other ones have to change to be in sync with what I've got so far. And so now you know that count has to change, so we'll make count go up by 1. And there's that bit of code. Hopefully that adds things on. How about if somebody says, take one off? What's the one that you want to remove?
The end one?
A, B, C, D, or E. It's a lineup, so the person standing at the front of the line is A, so that's the person that you want to take off the list. Okay, so people always go to the end of the lineup, always get added to the beginning. So we'll go into DQ, and we'll use Pfeiffer's rule of return statements. There's an E thing coming back. Let's identify what it is first. The one that we want to send back is what item? It's the front one. What are the words that give you the front one? Front is referring to that thing. But the thing that they gave you was not a node. They gave you that thing, so that's the thing that you want to give back to them. So this is front dot thing to store is the thing that you want to send back. Okay, so the item that's interesting here is front dot thing to store. When all is said and done, we're going to have to send that thing back. And now we're going to go and figure out what adjustments we have to do to make things right. So this guy doesn't belong here anymore. We've identified him, but it doesn't belong. What do you want to do to get rid of him? Well, he's no longer the front of the line. B should be the front of the line. To get B to need the front of the line, you need to skip over A, which means make front advance one person forward. The thing that advances one person forward is front equals front dot next. Okay, so we use that same notation for chains always or linked list. Front equals front dot next says just advance front one position, and now it's forgotten about the first one. Stepped right past them, and it's now referring to B. Okay, anything else that has to change? Count has to change. How about and? Haven't played with and, so it's fine. So by the way, notice that that's one thing that's sort of unique about queues that are different from a lot of the other data structures. In the case of a queue, there's one variable that's in charge of taking track of the and when you change things, you only manipulate the and there's a totally separate variable that's in charge of what's happening at the front, and you only ever manipulate the front and leave the end alone. So you're doing either or, but not both. Okay. Is that it? That's probably it. That's pretty much all the code, other than, gee, I wonder if it works for the special cases. So now we need a unit test. Do we have something we can steal already? We did when we built the array version. We said the array version has to match the general way of doing a queue. This version we wrote the same way to use the same words, use your queue words. Okay? So we can go and take queue array test and just do a little modification to it. So I dumped it into, it's still in that package. I'm just going to leave it as queue array test. Well, the only thing that's going to change here is that when you first build the thing, rather than building with an array underneath, you build it with a linked list underneath. So it's just a different way of storing things. The words are the same to talk to whoever's doing the storing. So it turns out that this set of unit tests, if that's the only place where we've ever said use the linked version, everything else on the left-hand side says just only do the general things that you can do. This test will also work for testing the queue version, or sorry, testing the linked list version. Okay, so ignoring whether or not we need to do special cases, we've got this unit test, so let's just turn around and run it and see what happens. Oh, it doesn't pass the tests. Okay? When it doesn't pass the test, you can go down to the failure trace and you can look at the very first one when it says null pointer exception, double click on that line and it'll take you to the reason for the failure. Okay? So reason for the failure is what? Null pointer exception. The only way you can get a null pointer exception on this line is if the end variable has a null in it. Because you've got nothing in it, you can't set the next when you don't have a beginning. So what's the problem? There's nothing on the list, so you can't chain something on to the end of the list because you don't have anything to chain onto. What do you want to do to fix it? What's the special case? If it's an empty list, so if for some reason the list is empty, which means count is 0. Now, by the way, in a lot of code and computer science textbooks, they may or may not have used that count variable, and even if they do use the count variable, you'll see that if statement written as if end is null, then do this. I don't particularly like saying if end is null, because when you see if end is null, your brain goes, null means there's nothing there, there's 0 items there, what do I do? And if you had to translate null into 0 in order to figure that out, to get the words right in your head, you just might as well have said what you mean. 0 means 0, there's nothing on the list. Okay? So it just tends to make the code a little bit easier to read if you just say 0 there. What would you do if there's nothing on the list? So let's draw that diagram. Now we'll worry about the special case. So we wipe out the middle case, which was the general one. There's the special case. We said that the first thing that the code does is make a new node to refer to A.
So it's going to be thrown in there.
How do you want to get it hooked up?
Front equals front.
Front needs to refer to that thing.
What does that mean?
And needs to refer to that thing. So if you're the first one on the lineup, you're both the front and the end of the lineup. And count needs to change from 0 to a 1. So if I'm the first person in the lineup, then I'm the front. I'm also the and count is now exactly 1. And this is another case where even though you could say count plus plus, I'd have to do the thinking of, oh, it was 0 and now it's 1. I'm being really explicit and saying, oh, it was 0, now it's 1. Okay? Then what? Special case means immediately put your return in there, say, I'm done. Don't let it fall through. We've left the normal case sitting where people can still see it. Well, if there's a special case for putting the first one on the list, I wonder if there's a special case for removing the last one. So if you get things down to where you've removed the last one, what do you have to do to make things right if you change the count variable? If you look on my diagram, I have this one thing on there. If I remove it and set it to 0,
There won't be anything to return.
what's wrong with the diagram?
Still pointing to something.
The front and end are still referring to something even though it's not in the lineup anymore. This won't technically cause a problem because when you go and re-add somebody the next time around, it will just, the code just quietly replaces front and end anyway, and this one will disappear then. But it won't disappear until the next time you add one. The better thing to do would be to make sure you set front and end to wipe this one out because now it's gone. that'll keep the code consistent. So in this case, front now needs to be null and end now needs to be null, and then we'll just fall through because we're done.
Wouldn't front already equal null just because of front button?
It might. This is one where it might already work whether or not you did it, but writing the code this way makes it a little bit consistent. Okay? They agree with each other, and then they're written sort of more or less in the same way. I worried about it adding. I should worry about it when I'm taking things off. Okay? By the way, so far we've had cases where the only thing that we've ever done for a special case is do the rejection style if, and then leave the regular code to do what it wants to do. Notice that this is probably one of the few times that I've seen where we did the work first and then we did some cleanup afterwards to make things right. Okay? So there's actually an entire pattern there. The entire pattern when you write code consists of reject the bad, do what you're supposed to do, and then fix things up afterwards to make sure that all of the other variables are consistent. Make things right afterwards. That's the entire pattern. So we've seen half of the pattern in the NQ and the other half of the pattern afterwards in the DQ. You'll actually see there'll be some cases we're going to write where you're going to see all of that pattern together at once. Okay? But that's the general little pattern that happens there.
Should you check at the beginning then to see if it counts through?
At the DQ, you don't really care because the question is, should I check to see whether or not there's anything there to DQ? The answer here is if somebody wants to DQ, they should check size to make sure that there's something there. And if they don't, it's just their own problem. They'll die, which is a good thing because they're trying to do something that they shouldn't have done. Okay? And so in this case, it's better if the code actually dies because now they can go, oh, I guess I shouldn't remove something if I don't have something. There's probably a bug in my code. If you just quietly make it go away and return some error thing, then you leave them with a bug. Okay, so there's the code. We'll run the unit test now and we'll see whether or not it works. And there we go. Okay, so it was the special case that was messing us up. Okay. And that's not unusual when you write code because quite often the special case is how you get things started. But I keep saying, don't write the special case first. Write the general case, get that to work, and then go back and say, well, okay, now that I figured out the general case right, that will help me figure out what I need to set it up for the special case to begin with. Something interesting about that code. What's missing in that code? What's not there that would hamper performance? There's no loop. Okay, so I said loops are a good thing in computers because they do things over and over again, which is why we want them, but they're a bad thing in terms of performance if you have lots of stuff to do. So in this case, there's no loop, so it's as efficient as it can possibly be. You're just basically chaining things onto one end or the other, and it's going to just be blindingly fast. Okay, so that's a good thing in this case. So the chain code is actually really easy to write once you get the hang of it, and it makes the problem fairly simple. And notice that we don't have to worry about queue size. In the array version, we had to worry about, oh, did we make this queue big enough? Is it going to hold stuff? What if it runs out? In this version, we don't have to do any of that at all. If I was worried about, if I really wanted to use the array version for some reason, and I was worried about running out of space, what would be a sneaky solution in terms of implementing an array version? What facility that's already there, array list, right? A queue is something where you always remove the 0 item and always add at the end. So you could use array list in here, and you could just say, make myself a new array list. Anytime something comes in, add, ArrayList.add, which is efficient because it adds to the end, and then ArrayList.remove the 0, 1 to remove it. Okay? Wouldn't be efficient for the removal, but it would give you the grow. Okay? What if you don't want to work with linked lists? We recognize now that linked lists are probably a better way to go for this type of problem. Java has a linked list class. In Java's linked list class, it has both a head and a tail pointer. The tail pointer is there to make the add really efficient. So in Java's linked list, it doesn't cost you to add anything to the end. It doesn't cost you to add anything from the beginning. So the easy choice is not to use an array list if you want to do things the queue really easily, but to use a linked list and just always say linked list.add and linked list.remove from a 0, totally efficient, and it's just one line of code. Okay? So you can build on by adding that middle level in there rather than working with arrays or linked lists directly, and that makes your code simpler because you're reusing a facility that's already there. Okay? But we did this just to show you that it was actually really easy to play with linked lists. By the way, the code or the midterm 1 from last year is posted in case you want to spend the weekend taking 50 minutes someplace and giving it a try. Okay, questions about queues and linked lists?
Is there a queue class?
Huh?
Is there a queue class?
There is a queue class in Java, but it's got a whole bunch of different strange variations. And we'll talk about why there's some strange variations in a minute. We'll do an application. But yeah, there's a queue class already in the libraries. Okay, let's talk about an application. Here's the issue with trying to come up with an application. I said that when you write this, when you deal with queues, I said it's usually a 2-player game, right? So I said when you think of a lineup, think of there's this person at the front who's busily, trying to take money for things and make the lineup disappear. And think of the second player in the game as the person who's standing at the end of the lineup, calling people and asking them to come and join, and their goal is to try to make the lineup as long as possible. And so what you've got is this competition with the person at the front end busily trying to do stuff, and the one at the back end busily trying to add stuff so that the line never runs out. Okay? So that's a queue is a 2-player game. So the problem with a 2-player game is to try to think of a solution I can show you where there's actually 2 pieces of independent code operating at the same time, which is something we've never done in any of our Java code, so we'll do it for this sample. Okay, so let's talk about a sample application here first. Here's the web server for CNN. Okay, it's taking a bunch of requests coming in the front end to process requests for what's going for some web page, right? Okay. What happens to CNN's web server if there's some big world event? All of a sudden it gets a ton of requests, right? So the old solution to the problem used to be, say, we'll get a mainframe and we'll just make a bigger, stronger single computer at the front end, and that will handle as many requests as we could possibly do. Okay? So option number 1 is buy the biggest computer that you can get, one computer, in order to process the requests as fast as you can. What's option number 2? Whole bunch of little ones. Okay, so if we put a whole bunch of little ones in there, people still need a front end to go to that's CNN. So where do you put the little ones? What does this one do versus the little ones?
Redirects.
It basically redirects them. So when people come in on this end and they want to talk to CNN, the main CNN server just has a bunch of little tiny servers someplace, right? And it just says, okay, we'll take this request, whatever it was, we'll send it off to that particular server, and we'll tell that particular server to respond to the user. If this one's busy and the next request comes in, we'll just go on to this one. Okay? But eventually what's going to happen is even with a whole bunch of little ones, you're gonna fill up the number of requests that all of the little ones can handle. If you have 1,000, all of a sudden it's really easy to get 1,000 people all at once wondering about some world event. So these things are gonna start to back up. So what do you do when these things back up if that's all that you've got? Can't buy any more at the moment. These things are starting to slow down because this thing wants to put the request somewhere.
Drop the oldest requests.
What does it doesn't want to drop any, so what does it start doing? Instead of this one being able to handle one, this thing, all of these are gonna start to back up. When they start to back up, that means that there's a lineup that forms of a bunch of unprocessed requests. Okay, and so the goal of the little server becomes to accept things in here and then turn around and either process them, or if it can't process them, it dumps them onto a queue, and then it's picking them off in order to try to get rid of that queue. Okay, and so what you end up with is a bunch of little servers that if they all get really overloaded, they all have this little queue of requests that they have to deal with. And if your computers all aren't the same speed, then some of them process things off the queue faster and return the results back than other ones do. And so you end up with some with 4 things unprocessed and some with 2 things unprocessed, but everybody's all still backed up. Okay? So what does the main server do now? If it knows things have started to back up, what's it gonna try to do with a new request that comes in?
Put it on the queue.
Put it on which one of these?
One that has the least amount.
The least busy of the servers, right? So find the server, talk to each one of the servers, find out who has the shortest queue, and then stuff the request onto there. Okay, so now the name of the game becomes, got one main server, it's got a bunch of little servers, they all have the queue of requests, and you push the requests onto there, and the main server's job becomes, who do I distribute this work to? Who's the least busy person at the moment? Even if they've got lots of work to do, we'll throw it onto their desk. Okay, so this is find least busy server, stuff the request, give the request to them. And in the meantime, while this thing is dumping things onto the end of one of these, each one of these guys is pulling the requests off the front of their queue as fast as they can to try to make this thing empty. Okay, so there's that competition, right? This guy is trying to remove all of them, and the big server is coming along and keeps stuffing things onto the end, and there's the 2 players in the game. Except that now we've extended this to, instead of 2 players in the game, we're distributing the work across a whole bunch of players who are all doing basically the same thing. Okay, so that's the scenario I want to end up with. Okay, so I'm not going to write this code. I'm going to show you this code because it's easier to explain than to write. So in the code, what I've done is I've said on this end, I'm going to pretend that I'm the 1,000 monkeys who are busily typing URLs as fast as I can at CNN to try to get it to do something. Okay, so I'm going to play the role here of trying to fill up all of those queues. Just me. Type, type, type as fast as I can. So that solves the problem of one player, but I want something independent to play the game of removing stuff. And so what I'm going to do to simulate that is I'm going to put a timer on this, and the timer is going to work independently. Every second the timer is going to go off. It's going to generate some arbitrary number between 0 and the number of queues I have. It's going to say, oh, okay, let me go take a look at the number 1 entry. If it's got anything at all, ask it to process a request. And so we're just going to make the timer every second pick some arbitrary one of these guys and throw an item off of their queue to simulate the idea of, oh, okay, it's somehow been processed. Okay, so this thing is going to be going off once a second, and I'm going to be typing furiously on the other end, and the timer is going to work independently of me typing. Okay, and in the middle of the game, every time I type something, I'm going to print out all the information about how busy those things are and what's being processed, just so that you can see that working independently. all in one program. So let's run the program first. In your code, it's this thing called Server Manager. And I happen to use the linked list to do it, but all of the main code is actually this Server Manager beast here. Okay? So, teach you something about how people read code. Ignore the constants. No use even looking at them. They're never going to change. Let's just jump right to the heart of the matter, which has got to be the main program. The main program just calls new server manager the constructor. That's done just so that you don't have the word static all over the place. All of the code sits in the constructor. There's the code for the constructor. Does a whole bunch of stuff. Okay? Let's just run it and see what it does so we have some sense of how it works. There's me playing the role of trying to type as many URLs as I can. I'm just going to type garbage here because they don't have to be well formatted in this case. And every time I type something, it tells me what the queues look like. So those are the things on the other end. Okay? And if I type a whole lot of them, every time I type some stuff, you'll see that the queues fill up in order, and then after a while, they keep filling up in order. And I've got a whole bunch of stuff because whatever the world situation is, it's really exciting. And then if you watch, the timer is still going off even though I'm not doing something. And you can see that the timer is trying to process those requests. So it's just picking some arbitrary one of those servers, 0, 1, 2, 3, 4, and it's just saying, oh, okay, let's pretend that that one handled a request. So if I type another one, you can see there's what the queues look like now. Doesn't look like my random picking is necessarily all that great, or else server number 0 is really fast, because it seems to be processing a lot of the stuff. But hopefully eventually it'll start just picking off everything out of the queues. Okay? So notice you get the sense that my hands are off the keyboard, but there's the person at the other end of the game trying to remove stuff. Okay? So now let's take a quick look at the code now that we understand what it's sort of attempting to do. There's the start of the code. That just says read from the keyboard. And I use the scanner class to do that because it's probably the best way to read from the keyboard. I have something that makes all of the queues that gets this game started out as empty, makes basically that diagram I showed on the board. And then there's something that says start servers, which is actually what needs to get the timer going to say, okay, let's pretend we're all ready to start serving the requests. The main loop of the program is straightforward. It just says, let's just pretend that this server is up forever. Somebody is going to be giving us a URL, so we'll go grab the next thing that somebody said to us. We'll stop the program if for any reason there isn't a valid URL anymore. That'll be the end of things. After we get a URL, we retrieve the least busy server, and then we turn around and say, hey, you can hold on to that request, which is exactly what I said in English. And then after that, there's my printout statement that says, show all the sizes of the queues. So notice the interesting thing about this main part of the program, no detail. And hopefully the words for the methods speak for themselves about the kind of actions that are taking place. So particularly we use the words find the least busy server and add that thing to the queue. Okay? And so there it is standing out all by itself. There's the regular thing that gets done as you're processing the requests. And the if statement there is a special case, just like it's supposed to be. Let's just take a quick look at what make server queues does. Make server queues has to make an array of queues. So there's not just one, each queue by itself pretends to be a server, so there's an array of queues in this case. To make an array of queues, you want to use new to make the array. Unfortunately, new doesn't work, so here's another weirdity about Java versus new of things. Instead, what you do is there's this array class, and you say to the array class, here's the type of object that I want to put into my array. Notice it says .class, which is a little strange. It's being very specific about here's the actual compiled object I want to put in, and here's the size of my array, which is the second argument. So you give it basically a sample. This is the kind of thing I'm going to put in my array. Here's how many items I want, and it gives you an array of those things back. Okay? So it does the same thing as making an array of things. It's just a really strange syntax. Okay? So after I've got my array of queues, then that array doesn't actually have any linked list objects in it. It's just variables. So that this thing just fills each one of the array positions with one of the queue objects. So now I've got an array that's referring to a bunch of queues. Get URL just uses the scanner class. Oh, by the way, notice that in this thing, even though it's a fairly complicated idea to try to read the user input, there's no nested if statement. So I'm using rejection style to kick things out all the time. So I ask the user to enter a URL. If there's no line that they've typed, we're done. If there is a line that they've typed, go check it. If it says quit, we're done. If it says anything but quit, we'll take that and we'll stuff it into a URL object because that must be HTTP or whatever. Okay, so fairly straightforward, a little bit of error checking to read the thing. How do you find the least busy server? This is, I think the first one is the least busy I've seen so far. Let's go through all of the rest of them, starting with the number 1, because I did the number 0, 1 already, and let's see if I can find one that's bigger, or sorry, in this case, smaller, has less items to process on it, then that's the least busy one I've seen so far. And eventually, when I find the least busy one, I say, hey server, here's the index position of that one, or actually return the server. Show servers just goes to for each to print out all of them. The interesting thing about this code is actually how the timer works, because it's the most fun thing that you've probably never seen before. Okay, so here's how you do a Java timer. There's a timer object, and for the timer object, you say, here's the interval that I want you to repeat. That's actually in milliseconds, so I've got it set to repeat every second, whatever the constant is. So that says, every second I want you to wake up, and when you wake up, here's the object that contains an action performed method that you should use every time the timer ticks. Okay, so this is like a click listener. Like if you would say, if somebody clicks on a button, here's the action that I want you to perform when they click on the button. In this case, we're saying if the timer goes off, here's the action that I want you to do. In Java, the thing is that you can't link up a subroutine directly to something. You have to pass the object that contains the method. And so that's why here, when we first make it, we're passing a new server object that contains the action perform method that's going to do all the work. So as with anything that says a listener or an action performed, that's where all the good stuff is. Every time the timer ticks, once it's been set up, it goes and picks a random number of 0 through however many servers I have on my array, picks that one out of the list, and as long as it's got something on it, it just calls dequeue to say get rid of it. So there's the dequeue from the queue to clean it off. Okay? And so there's this idea basically that the queue is, one side of the queue is handled by the scanner class and me doing the typing, and the other side is handled by the timer working independently, coming along and saying, oh, timer popped, let me find a queue. Here's the least busy one. let me do a DQ off of that one if it's got anything done. So this code is useful for you more so that you can steal the timer class stuff now that if you ever happen to need one. Okay, and with that, we're done with queues. Next on list for a little bit next week, we have Monday to do something new. Tuesday we'll go over last year's midterm. Wednesday will be question day, and Thursday's midterm day, right? See you later.